Often when we're doing hypothesis testing, we use what's considered the traditional method to make our decision about our hypothesis test. Now, after we've read the problem and then we've written down what our null and alternate hypotheses are, the next thing we need to do is make sure that we're getting the information for our critical values off of the correct distribution for the parameter that's involved within the hypothesis test. And making this decision and finding out specifically how we use the tables or the calculator options in order to find these critical values is an important key to determining what type of a problem that we have and where we're going to set up the numbers for our decision. Now, I've given here several different examples where we have hypothesis tests on different parameters, and often these are done within the same unit of the work on hypothesis testing. And looking at these, how do we make our decision, and then how do we find the critical values for each of these types of tests? So let's look at these examples. The first one is where we have a null and alternate hypothesis, where involved in the hypothesis testing, we have the population standard deviation. So we have sigma here is equal to 9.3 as our null hypothesis, and our alternate hypothesis is that sigma is different than 9.3. So this is a hypothesis test concerning the standard deviation. Now, we don't have a specific distribution that the standard deviation follows, but we do have a distribution that the population variance follows, and that's the chi-square distribution. So when we're doing a hypothesis test about the standard deviation, we're going to go through the chi-square distribution of the variance in order to get our critical values and to do the rest of the test, because the variance is the square of the standard deviation. So it has that link where we can go through it in order to get our critical values and to do our test. So when I'm thinking about the chi-square distribution, remember the chi-square distribution is one that's skewed. And with the chi-square distribution, we have, this is a distribution of the square of a real number. So the values along the number line for the chi-square distribution are always positive. And I also don't have symmetry that I had with other distributions that we used. So in this situation, I have an alternate hypothesis that's a not equal to. So that means that I have a two-tail test. Remember, we decide what tail of a test we have by the alternate hypothesis. I have a two-tail test. And the significance level is the amount that I have in terms of the values within the total combination of the tails of this test. So since it's 0.05 that's shared between the two tails, I need to have a 0.025 at each tail. Now, in the organization of the table for the chi-square distribution, most generally those tables are organized where it gives you from the cutoff value area to the right, which is different than what we've seen on other tables. So we have to be careful to always read the top of whichever table we're referencing to find out how that's been organized. Now, when we go from the cutoff value area to the right, we would look underneath the 0.025 column. And then along the edge of the chi-square distribution, you'll see your degrees of freedom. And the application that we use in terms of the chi-square distribution with hypothesis testing with one sampling, we have our degrees of freedom in this case is n-1. So I have degrees of freedom of 28 minus 1, because my n is 28, which is a degrees of freedom 27. Now, if you refer to a table that's the chi-square distribution, look under the column heading of 0.025 and look across from 27, you'll see the number 43.194. And that gives us the critical value for the right tail of this two-tail hypothesis test. To get the critical value where we go between the not reject and rejection region on the left tail, we need to think, well, what area would be completely to the right if I have a 0.025 in my cutoff value and then to the left? Well, since I have a whole area underneath the distribution to be 1 or 100%, 1 minus the 0.025 would leave me all of this area forever right. In that circumstance would be 0.975. And when you look under 0.975 across from the 27, you'll get the value 14.573. So the 14.573 and the 43.194 are the critical values for this hypothesis test. And that's all this question asked. It didn't ask us to do the entire process of the hypothesis test, just to make sure we know where the critical values come from. Let's do the next one. The next one is a hypothesis test, again, concerning the population standard deviation. So we'll go through the distribution of the variance to do this hypothesis test, which again is the chi-squared distribution. And we have our chi-squared distribution is skewed. In this case, my alternate hypothesis is that the standard deviation is less than a number. So less than is a left tail test. L less than L left is a memory device you can use for that. And since the way to read the chi-squared distribution talks about looking under the heading where it's area all the way to the right, my left tail here is my alpha, 0.01. So my area to the right of that is 0.99. So when you look under the heading of 0.99 and across from your degrees of freedom being 9 subtract 1, which is 8, you'll see the number 1.646 for that critical value. Let's go to part C. In part C, notice the population parameter that we're doing in this hypothesis test is the population proportion. Now the population proportions distribution, as long as n times p is greater than or equal to 5 and n times q is greater than or equal to 5, is the normal distribution. So I'm going to draw now a symmetric curve for my normal distribution. And remember, with the normal distribution, I had 0 in my standard normal curve as the mean. Numbers that are critical values to the left of 0 are negative, and numbers that are critical values to the right of 0 are positive. This is a less than, so this is a left tail test. And I have 0.04 in my left tail. And our n is 50, but we don't have degrees of freedom with the standard normal curve. So we have our 50 times, if we did a p hat value times our 50 and a q hat value times our 50, we would see that each of those would be greater than 5 working with this. So I'm going to look at this one being the normal distribution. So we would either use the Z table, or if you're using a graphing calculator, you could use the inverse norm option under your distributions key. And the inverse norm option is always looking for you to input area to the left of whatever your critical value is. So since this is a left tail test, area to the left of my critical value in this situation is going to match the same as the alpha. So inverse norm, my area to the left is 0.04, and my mean of my distribution is 0 because we're looking at the standard normal curve. My standard deviation values in the standard normal curve are 1. And when you enter all that information, you'll get a critical value of negative 1.75 for this one. Part D is next. Part D, we're doing an alternate hypothesis, a hypothesis test about the population parameter mu. Now with mu, I have to find out whether I know the population standard deviation or not. Because if I'm doing a hypothesis testing concerning the mean of the population, and I know the standard deviation of the population, I use the normal curve. If I don't know the population standard deviation, but have to use the sample standard deviation information, that's when I have to use the student's t-distribution. So I keep looking, and I see here it's sigma is equal to 2.75 in the given information. So I know the population standard deviation while I'm doing this hypothesis test about the mean. So this is then the normal curve that will give me the critical values. So I'll again draw my normal curve. In my alternate hypothesis, it's a greater than, so it's a right tail test. My alpha is 0.01. And so I look and know that if I put this into the inverse norm, it's looking for from the cutoff forever to the left of that. If 0.01 is in my right tail of the curve that I've drawn, then 0.99 is the area to the left of that. I have a total of 1 underneath. So here we're going to go inverse norm of 0.99, comma 0, comma 1. And you'll see that you'll get a value of 2.33 for that critical value. Now lastly, I have a hypothesis testing concerning the mean. So then I look at the rest of the information and notice I have S is equal to here. So I have to use the sample standard deviation because I don't know the population standard deviation. So that's where I need to use the student's t distribution for my critical values for the hypothesis testing in this situation. I still have a symmetric curve, it's just a little bit thicker in the tails. I have a greater than for my alternate hypothesis, so it's a right tail test. My 0.01 is in the right tail. The student's t distribution is symmetrical, about a mean of 0, just like the normal distribution was. And when you look at this, usually we have to use a table for looking this value up. It has degrees of freedom as well. That's n-1 in the sampling from a single group for this case. I have 31 as my n-1 gives me a degrees of freedom of 30. And so when I look underneath the heading of area in one tail of 0.01, down until I'm across from my degrees of freedom being 30, and realizing that the tail that I'm drawing is to the right of 0, I have a positive 2.457 that you would get for the critical value here off of your t table. So these are several different examples where you are asked to find just the critical values to make sure that you're on the right track in terms of working with the correct distribution depending on which population parameter you're doing your hypothesis test on.